Welcome to this 2017 Pre-Cal semester exam review. Now, but when you are looking at this video, I do want you to do one thing after you're done, because this one's going to contain all the solutions. So with this, it's going to be very important you're able to do 3 things after you're done. And the only way you could really discover, and one of the things I love is to really test yourself about this, it's going to be important to write it again and redo the problem. And you could only guarantee yourself that you're doing it right if you're able to remember and understand afterwards. And last thing is be able to apply. If you could do these 3 things successfully, then you could go ahead and actually walk in with a lot of confidence and guarantee yourself that you'll know how to do the majority of the exam. Now, let's go ahead and start with question 1. It says convert the degree minutes seconds form and round. Now, one thing we have to remember is that 1 degree contains 60 minutes. So one thing you see right here is you take the 0.96 that you see here, you multiply by 60, and you discover this solution. Now, the thing that's important is that this right here becomes your seconds. And you're going to take the 0.6 and then multiply by 60 again, because 1 degree equals 3,600 seconds. And if you notice, 60 times 60 is 3,600, so when you take the 0.6 and multiplied it, it's been multiplied by 60 twice, you discovered the 36, so your solution comes out being 81 degrees, 57 minutes, and 36 seconds. All right, now it's question 2, convert angle to degrees. The most important thing you have to remember here is this formula, that you have to multiply your radians by 180 over pi. And the thing that I love is it's really easy if you had to do the other way around, degrees to radians, it's just pi over 180. But the pi's cancel, and you end up with 60 degrees. Now let's look at question 3. They want you to find the exact value. Do not use the calculator. The easiest thing to do is make it into a proper fraction. So that means that you create it to 3 1/3 pi. And the part you're focusing on is a 1/3. So let me bring out the unit circle. And actually, well, a little bit. Let me explain with the unit circle what is happening. Remember, this is pi. This is 2 pi. So 3 pi is going to be all the way around. So once you reach here, which is the 3 pi, you travel 1/3 pi. So you look at this one to kind of figure out where 1/3 pi is. And that's how you know you end up here. And then it's asking for cosine. So the cosine is the x value. So that's how I know I could guarantee you that point. So let me, wish there was an easy way to undo on this one, but it doesn't. I have to manually kind of delete them all. All right, I'll just work around it. All right, let's go back over here. Oh, actually, not this one. This one right here. Okay, so we're going to do the similar tactic on this one. The only thing is that this one we're going to cover 1/4 pi. So we'll go back to the 1 unit circle. 5 pi over 4, actually, in itself. Oh, come on, where's my little writing utensil? Good, I'll switch color. It's also here because anything that's kind of like odd ends up there. And then 5.4 pi ends up there. So when you're discovering the solution for, let's say, like in this case, oops, I'll take away that one. In this case, pi over 4, we're going to be traveling just pi over 4 here. So this is the actual amount, and this is the value, which is square root of 2 over 2. So that's how we end up with this solution. And now with tangent of 750 degrees, we're going to think 1 pi is 360, so 2 pi's is 720, so I subtract that. So tangent of 30 degrees, which is all the box values on the outside of this circle, is how I'm able then to guarantee you that that's the solution for that one. All right, now let's go to question, next page. All right, now in working on the next page, it's going to be important that you do Sohcahtoa. And the reason being is because you're given x and y values. And because of that, you could build a triangle based off the x and y values. The angle's here, so I based the -3 and 4. And one of the benefits I have is that I know that this is a 3, 4, 5 triangle. If not, you could do Pythagorean Theorem to solve it. But because we're working with cosine, it's important that cosine is adjacent over hypotenuse. And this is how we end up with the solution, -3 over 5. Now, when it comes to tangent, tangent is opposite over adjacent, which is the same thing as y over x. This is x and this is y. So this is the reason why you see square root of 77 over 9, which is the y value, and you also see 2 over 9, which is the x value. So after you, one thing that's important is that when you switch it here, when you're dividing fractions, very important to remember that you got to reciprocate. And then from there, once you do the reciprocal, we discover the nines cancel out, and this is how we end up with the solution, square root of 77 over 2. On this one, same thing, Sohcahtoa. But in this case, one thing to remember from Sohcahtoa is that we're looking at the, like this is related to sine. Sine theta is opposite over hypotenuse. So the reciprocal of it is going to be hypotenuse over opposite. So once we make the discover that this is negative 5 over 2, we have the power to build a triangle because they tell you quadrant 3. So quadrant 3 being here, I'll do 5 and negative 2. We do all this. This is all Pythagorean Theorem to solve for the other missing triangle side. Oh, one thing that I missed, it's very important. Hypotenuse is always positive. So in this case, we have the power to move the negative 2 in the numerator denominator spot, so we move it to the denominator spot to place that as negative 2. But once we do all this Pythagorean theorem, we discover that the other missing side is square root of 21. So that gets placed here. And then with that, we're being asked for cotangent on question 2. So the cotangent is adjacent over opposite, and we have those values. We end up getting square root of 21 over 2. On question 9, one thing that's important to keep in mind, and sometimes confuses some people, well, one thing that we know, cosine is adjacent over hypotenuse. So the thing that I love is that we have the solution for adjacent over hypotenuse. But then a lot of people get confused with this now. If I go back to the unit circle, let me show you something. All the tangent values here are positive. All the ones are here are negative. So your value is, and this thing specifically states, when tangent is less than 0, so all the negatives. So we discovered that at quadrant 2, tangent values are negative. Also, if you look at the unit circle, quadrant 4 will have it. Well, we are given the adjacent, the 3, and the hypotenuse side. So through the use of Pythagorean theorem, we'll get up to square root of 40, and then I simplify square root of 40 by breaking it up, square root of 4 over 10, and this is how I end up with 2 square root of 10. Now, let's go ahead and move on to question 10. From here, cotangent is, one thing that's important to remember with this one, cotangent is y over x, and that's because it's anytime adjacent, opposite over adjacent is tangent. So let's start from the beginning. Opposite over adjacent is a tangent. So discover that cotangent is adjacent over opposite, is reciprocal. And adjacent is also typically known as x, and this is typically known as y. So this actually should be reversed. Cotangent to be. So like the work process you see here, let me go ahead and fix this. Because this should not be here, so don't follow this. But what I do want you to follow is this. Cotangent theta is going to be then, if this is, one thing that's important to keep in mind is that this is then cosine theta over sine theta. And that's because we made the proof that it's x over y from the cotangent value. So then we have that this solution then is 2/3 over square root of 5 over 3. This is going to lead to 2/3 multiplied by 3 over square root of 5. 3's cancel out. We're left with 2 square root of 5. We have to rationalize the denominator anytime we have a square root, so we multiply this by square root of 5 over 5. And we'll discover the final solution is 2 square root of 5 over 5. All right, now for question 11, it says, for what values does sine square root of 2, positive 2 are solutions? Well, we got to go back to the unit circle. Remember, sine is y. And I'm going to point out pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 all produce either positive or negative square root of 2 over 2. So in essence, if I go ahead and I look for, and I ask you, find out sine pi over 4, you're going to tell me positive square root of 2 over 2. And the same thing would happen with 3 pi over 4. 5 pi over 4 actually produces negative square root of 2 over 2. But these are all solutions that actually produce this value that's here. And that's what's important to take away from this. And when you're looking at these values, like when I look at this, you see how I got positive there? It comes from the positive 5 pi, from pi over 4. This one comes from here. This one's already shown, and negative square root of 2 over 2 in the y spot. proves the solution of 7 pi over 4. All right, and then the next one is it asks, when is tangent theta not defined? So going back to a unit circle, I'll discover two places for that. Here, you see how it says undefined there, and then 3 pi over 2. At the bottom will say undefined as well. So that's the reason why on this one, the two solutions are pi over 2 and 3 pi over 2. All right, now let's move on to this one. They want us to graph the equation of the circle. One thing, if there's nothing around the x's, we are guaranteed that the center is 0, 0. And then the radius is 6. Now, one thing to remember, I came up with that solution because in the equation form, this is placed as r squared. Remember, it's like normally like that. But in this case, r squared is equal to 36, which guarantees me the r is 6. And then from there, you just move 6 on either side. And you get that solution. Now, small corrections on the directions on this one. It says that this one graph the following circle. And really one of the things I did is that I went ahead and brought up the standard form with the h's and k's and the r's. And the thing that's important is that you substitute it all in, as you see here. The final equation comes out being this. All that really happened is the center got moved here to this point, and radius was 5, so we counted 5. We went a little bit off grid because it's a little bit larger than what has our graph area. Now for this one, they want you to find the exact value of 2 pi over 3. Now that's pretty simple. All you have to do is take out your unit circle, discover 2 pi over 3, and I think they were looking for the sign value. I think that's the reason why they came up with the square root of 3 over 2. Let's confirm that. Yeah, you want a sign. That's how they came up with the solution, square root of 3 over 2. Now with amplitude and period, questions 14 and 15. One of the things that we studied, and one thing that was important, is we had this acronym called OFFs. And it was very important because these four things will do a movement up and down, like vertically, increase it, what we call, or compress it, which we call the amplitude. Frequency was also important. That's how much it takes to build a period. Actually, frequency affected the period, better put. And S was the starting point. So like in this case, 1 is my amplitude on this one, so this is the reason why you see this solution. Period, with sine and cosine, you have to travel 1 unit circle in order to complete 1 cycle, which is 2 pi. That's the reason why you see 2 pi over f. So once we made the discovery that f is 3, then it's pretty simple solution, 2 pi over 3. Same concept with 15. Amplitude right here. Frequency was this one, and for period it affected this way. We have 2 pi over negative 8 pi over 7. So one thing I want to point out, reciprocated this. This was originally 7, 8 over pi. Then I cancel out the pi's with that one. Cancel out the 8, made a 4. Cancel out that 2, made a 1. And the resulting answer was negative 7, 7 over 4. All right, now for these over here, same thing, just bring up 2 unit circle, find the exact values of cosine of 3 pi over 4. Cosine 3 pi over 4 is way over here. That's it. Negative square root of 2 over 2. That's why you see negative square root of 2 over 2. And then when we look at the sine of 7 pi over 4, bring up the unit circle again. And it's right here as well. So negative square root of 2 over 2. So in this case, it coincided with the same solution. Let's move on. Now, with this one, they want us to graph the ellipse. They also want us to discover all the center vertices and everything else. Now, one thing that's going to be guaranteed to us, the bigger denominator tells us which one's the major axis. So this one tells us the major axis is there. And also tells me what value is A. Because A is the one that also has the vertices to it. So once we discover that A squared is 16, then I could prove to you that A is plus or minus 4 when I graph it. So that's the reason why you see 4 here. And 4 over here too. Afterwards, B, we discover it's 3 because B squared is 9. And this is why you see 3 here, from here to here. Last thing we had to use is this equation right here. C squared is A squared minus B squared. And that guaranteed me once I substitute the values for A and B, which I had the power to do so, I come up with the solution that C is plus or minus 2.65. Oh, this is 2.265. All the answers you see here actually came from the graph. And this is the best way I could guarantee, or the easiest way for you to come up with the solutions on this one. Now this one, they want you to graph the following ellipse. I went ahead and they gave you a vertice, and and they give you b over 3. This one actually had multiple solutions depending on what you wanted to do. I decided to graph the vertice, and then this c, I made it up. The only thing that was really required if you're given a vertex in the b value is you got to make sure your c value or your a value from here to here, like I picked it to be 6, just needs to be bigger than your b. A needs to be bigger. So it kind of looks like this. A is bigger than B. If you want to look at that, but that's what I was trying to communicate across. But the discovery of it is that once we have A and B, then we have an ellipse that works. And then everything else we have, like the foci right here, how to come up with that. Oh, I didn't actually write the final equation on this one. Final equation on this one will then be x squared, because I decided to make the major axis this way. Very easily, somebody could actually have done it the other way around, made the major axis through the y, because you had the power to pick the center, just had to be bigger than 3. So we would pick 4, whatever it was. This was 36 plus y squared over 9 is equal to 1. So that was your equation. All right, let's go ahead and move forward, and let's go to question number 22. Okay, now with this one thing that was important when you're working with these is just make sure that when you work with the law of sines, law of cosines, that the triangle always has it that A goes with alpha on an angle, B goes with beta, and C goes with gamma. And that's what you see here. Afterwards, you fill in the values. Like I put 33 here, 17 here, and 15 degrees here. And one thing that if you're given side-side angle, you normally work with the law of sines. Now, there was some other examples where we work with triangles, special triangles, that we were given other things, and sometimes we have the law of cosines. Now, one thing that we're guaranteed with the law of sines is that you had this proportion, and in this case, we were given sine beta, which is 15 degrees over 17, and this one. The easiest thing you got to do is cross multiply and divide. Once you do that, which is 33 times sine of 15 degrees divided by 17, you come up with the solution right here. Afterwards, I applied this sine inverse for the purposes of coming up with the degrees. Now, I got this degree value only because my calculator is in degree mode. So you got to make sure that you do this in order for you to come up with the solution. Make sure your calculator is in degree mode, and then you'll be able to come up with the solution as well. All right, now let's go with these over here. Now these I want you to find the vertices, foci, and everything else. Deal with the equation. I graphed them. You can come up with the points from here. The thing that is important to remember is that this is major axis on the x-axis. So I discovered A is 5, B is 2 from the use of A squared, everything else. And you see it here. Center is also in the center, but this is 5. And very similar to like the other one before, just more practice. This is 2. Foci was this amount by using A squared plus B squared. Actually, I probably should bring it down more because I want to say I have the solutions there. So like 4.58 is the value here. But I want you to try that. Same thing with this one. This one, the thing that was different about this one, you had to divide by 36 all the way through. And once you did that, you discovered that the solution, when you reduced it, was 9 over 4, which, now one thing that's interesting, they switch into x and y. So you got to make sure that you recognize that this means that the major axis is on the y-axis. That's the reason why you see all the bigger links on that one. But everything else is the same. Now this was actual circle, but if you divide by 4 made it into like an ellipse form, it was a special type of ellipse, which is a circle. So one thing that's guaranteed is the radius is 2, foci is 0 with that one. Now with these over here, you were given points, and you're asked to discover what the equations were. Now, one thing that's important, once you graph the points, like you're first given center in that vertex, this guarantees you that from here to here, A is 3. If they tell you it's a vertex, then you have the A value. So with the A value, you're able to come up with the A squared value, which you need for the equation down over here. So you see the ramification comes all the way through. Now, the other thing you're given is that you're given the foci. So you're given C is 1, which gives you C squared is equal to 1. And then you have the equation, C squared is equal to A squared minus B squared with ellipses. And this is how I was able to discover the B value, which gives me from here. It's pretty much similar here, except that this one gave you the length of the major axis was 8, which means that this from here is 8, which guarantees me from here to here is 4. And that's how I came up with a is 4 and a squared is 16. And we were also given the foci point. It was important and annotated it was here. So if you notice, the a squared is actually right here with the 16 underneath the y. And then through the use of the other equation, c squared, this one right here, I was able to come up with that this solution is 12 using the math that you see here. This one, you're given vertices, you're given y-intercepts, you're actually given a and b. So from there, you're actually able to come up with the equation, and also with the foci, which is right over here. All right, now let's go ahead and move on to question 30. Question 30 had to do with the sum and difference of angles. And we were given simply two pieces of information. Sine alpha, quadrant 2, sine beta, quadrant 3. As the previous examples, I'm able to build this from this. And then from here, this work that you see here has to do with the Pythagorean Theorem to find out the rest of the triangles. Only reason I needed that is because I needed to come up with these solutions right here. Well, this one was given, but I needed this one. This one not so much, but I needed those two for here, as you can see, cosine alpha. And the 513, that one was given, so that one was great. Now, in this case, this piece of information gives me the power to build that triangle. See, it says quadrant 1, you're given this. This one was easier because there's a 3, 4, 5 triangle, so you don't see any work. But this information gives me the power to come up with sine and cosine values, which I needed here and here, and then I multiply it all together. These two denominators make up to be that. These two, you multiply those two fractions, make up that fraction. My final fraction is here after I solve for it. Something similar with 31, but not so much work. You're given only this piece of information. You got a triangle, you got sine, you got some trig with some values, quadrant 3, and this produces this here. And once you have that, then you're able to come up with the missing side and come up with all the trig values that are needed. You're able to come up with sine, cosine, and tangent, and that's all needed to produce these equations. You see how it says sine 2 alpha equals 2 sine alpha cosine alpha? Well, I got sine and cosine alpha right here. That's why you see these values here, and the solution being here, negative 240 over 289. And then for the second one, we have this equation. We're able to square it, but if you see the math and you follow through the math, you'll discover that we'll come up with this solution right here. But same thing, same concept, all came from the same information we were first given from here. All right, let's go ahead and move on, and let's move on to the next questions. On question 32, they want us to convert from rectangular coordinates to polar. Now, the first most important thing to do when you do this is to plot. I have the power and the benefit of knowing this quadrant 2. Remember, all polar coordinates are given an r and angle value. So we have to find the magnitude. This is r. And I also have to find the angle. So I'm doing this first. I need the r value. The thing that becomes easy is that r is a simple equation. R is equal to square root of x squared plus y squared. So with that, we're given the power then to use that to come up with the square root. 8 squared plus 8 squared is square root of 28. And this reduces to square root of 16, which is 4, which ends up being 4 square root of 8. Now the next thing we got to do, we're going to go ahead and discover what the angle is. And typically, if it's in quadrants 1 and 4, you just use this. I put this plus 180, and I put this explanation because this one's in quadrants 2 and 3. And the reason why that's important is that calculator does not give you solution in quadrants 2 or 3. So we got to add this 180 here. That's the reason for this. So this, I think, comes out being like negative 45 plus 180. That's how I discovered that this is the right solution. And this comes my polar coordinate to graph that same rectangular coordinate using polar measurements. All right, now let's go ahead and now use this next one. This one is we'll move on to vectors. Make vectors, what vectors were so unique is you can start them anywhere. And i's and j's are the same equivalent as this kind of component form written down. So it's easier sometimes to ignore the i's and j's, just write in component form, knowing that this is a directional value. That means that no matter how you draw this vector, you're going to go, I was horizontal, 3 was vertical. Horizontal, vertical. So, but the important part was this. Negative 9, 2. That one thing that I love about vectors is that you had the power to pretty much just almost like treat them as a distribution. So that's the reason why you see the solution 6 and 9. And same thing here. Now, I applied the negative in this case because afterwards I could just apply plus here. And you got 36 over 8, and then you just add them. So 42, 6 plus 36, 9 and 8, 17. And there's your solution. Now this one was finding the magnitude. Sometimes you have to find like how much actually the length of it is. Easiest thing to do is break it up in components. So like this is vector v, this is vector w. We're subtracting them, so we come up with this. I decided to distribute the negative here. That's the reason you see this over here, so I can make it plus. And then afterwards we came up with this new vector, but we're also still discovering the component to it. Sometimes you draw one-line twos. The most important thing is you understand that that's what they're looking for. The component, or the come up with the actual magnitude, was a simple equation. It was just a squared plus b squared, square root of it, because we have ai plus b letter j, and then vector. And the thing that I love is made it easy because you're not having to do anything else other than input and then come up with the solution, which was square root of 122. All right, let's go ahead and move forward. And next one. Okay, so another conic. Now with this conic was slightly different. I want you to graph. Center was off. We discovered that the major axis was on the y. So that's the reason. And once we made A5, this is how y, when we graphed the center, the vertex was here. The b was 2, so you see a distance of 2 here. That's 5. Foci was like 4.58. The same, pretty much same concepts, but just reworked. And the next one, 36, this was a hyperbola. Now hyperbolas are a little different. It had vertexes too, but one thing that was unique about them is that they contained a minus that made them open up or down. They no longer were touching each other. It was like separate. The A is always the one that was positive. That's guaranteed. So like in this case, b squared we discover is 9. So from here, I can now guarantee you that's plus or minus 3. So from the center, that's 3. That's how I come up with the vertex. That's 3. That's how I come up with the vertex. And then the focus was a little different. Focus was actually a c value, which is the same as before, but the equation was now almost like it was Pythagorean Theorem. C squared plus a squared plus b squared. So with hyperbolas, it was exactly what it was. And this, when 9 plus 16, you see the math, you get 5. So that's the reason why this is 5. This is 5. Now the b was important, but it was actually just important to draw this box value you see here. Because with these, you have these asymptotes, and like in this case, this asymptote will produce 3 over 4x. So from here, from the center, I went up 3 over 4, point there, up 3 over 4, point there. And the same thing over here, up 3 over 4, and all the sides, and then I draw my actual asymptote, as you see there. So if you want to rewind the video and see with all these marks, you could feel free to do that. All right, let's move on and look at the next one. Oh, this one was the parabolas. Now, one thing that was unique, one thing that was new with parabolas that we're really teaching is that we had focus point and directrix. Focus was discovered by finding this a value, and the a values was actually hidden right in here with this 4a. So one thing you'll notice is that, look at this. You see how it says 4a equal to 16? When we divide it by 4 to both sides, this is how I'm able to come up with a is 4. And then guarantee you, since I know this one opens to the right because it's positive, that's the reason why you see this 4. I came up with these 2 auxiliary points from doing this work here. Because all you do is we're looking for 2 other points on the graph where the focus is at. So you just got to put it in. If x is 4, what 2 points do I have? And that's how you come up with that solution. Now the other thing that was new is Directrix. Directrix was always opposite of the focus, exactly the same length. So this time it was x equal to negative a. So it was x equal to negative 4. So that's how you came up with this point here. Now this was another parabola. It was just not in the right format. So one of the things I did is I wrote it out and I started solving for it. And one thing that I discovered, multiply by 8, those are the two transformations I made. I came up with this. Now this one means I have a vertex that's actually different. Vertex is going to be, since this is h and k, my vertex is 2, 3. I still had this a value that I had to discover. Because we still had the same property of 4a is equal to whatever value you see in front of the one that's not squared. So we made the discovery that was 2. So when I graph my vertex, that's 2. Directrix is 2. So that's how I discovered that the directrix was actually the line. In this case, y equal to 1. And focus was, in this case, it was 2, 5. Easiest thing to do is graph it all and come up with the solutions. And then it just opens up. All right, let's move forward. We do logs. Now, with logs, we discovered this thing called log loop. Very important because one of the things that's important that I want, before you leave my pre-calc class, I want to make sure that every other math class, exponents know this. Very important. Exponents and logs are related because they are inverses. But that related because they're inverses. So that means that being inverses, one could be switched out to the other form. And one of the things that we discovered is that we have the power to do this log loop. Start with the base, picks up this as a new exponent, and then pushes the x out in that spot. Like in this case, log 7 base 23, x in that spot. Same thing here. X picks up this 11 as its new exponent, pushes the 13 out in its spot. So we call it a log loop. You could keep on doing it over and over. Question 41, they wanted to solve with you to change a base. That means you use log of 125 over the log of base, and you come up with that solution. And then they want you to solve each of these logs. Some of these, you have to just look at it and recognize. If the log is by itself, you have the power to the log loop. Like in this case, you can take the 5, log loop it around. So this is how I end up with 5 squared is equal to push out to 3x plus 4. We start solving for x, and this is how we get x equal to 7. Now, with this one over here, if you have logs of the same base, it's like if you almost cancel them out. Now, you typically don't cancel it, but the only way that that could be true, that statement you see up there be true, is that you need to equal each other. That means 3x plus 7 needs to equal 5x minus 3. So this is a multi-step equation. You move all the numbers on one side. So I decided to move the 3 this side. I decided to move the x on the other side. So this is how I end up with 2x is equal to 10. Divide by 2 to both sides, and then I discovered that x is 5. Now let's move on to the last couple of ones. All right. Ooh, you know what? I think I want to say there was another one from here, right at the bottom. Let's see if that's true. Oh, no, that's it. We just had the solution on the other side. It worked for it. All right, so for question 44, I can't do a log loop right away because I need to first move the 6 that you see here. So you see minus 6, minus 6. This produces 12. Now, when I do the log loop, I end up with 2 to the 12, which comes out being a big number, 4,096, and that's fine. I add 2 to both sides, and I come up with the solution, 4,098. With question 45, we go ahead and instead of subtracting, that's a multiply. So as soon as you see divide by 3, divide by 3. Now I isolate my log, and now I could log loop. New solution is going to be 2 over 6. The same thing as before. Love the fact that we come up with x equal to 66. Now question 46, last question on this. You have to be able to recognize if you have a base of 2, the only way you can really solve this, and then guess and check, is to actually try to convert the 512 to a base of 2 also. And one thing is that 512 is guaranteed to be 2 base 9. And once I make that discovery, we have the same basis, just like the other one. They don't technically cancel out. But the only way that it could be true is if 3x plus 3 is equal to 9. And we solve for x, so we subtract 2, subtract 3, and then divide by 3, divide by 3. And we get this x equal to 2 solution you see here. All right, hey, listen, good luck on the final. Hope this helps. And if anything, just remember, keep on practicing until you master it. Rewrite the questions until you master it. Thank you for watching.